Look up at the night sky on a clear evening. What do you see? A scattering of stars, perhaps a planet or two, the gentle arc of the Milky Way. It feels peaceful, almost knowable. But that feeling is an illusion, a trick of scale and perception. The truth is, we are adrift in a cosmos of such staggering immensity and complexity that our most brilliant scientific minds have only just begun to map its shores. For every question we answer about the universe, a dozen more profound, more baffling mysteries emerge from the darkness, challenging the very foundations of what we believe is possible. These are not simple puzzles waiting for the right equation. These are cosmic enigmas that defy explanation, phenomena so strange they seem to whisper of realities beyond our own. This video is an invitation to step into that unknown, to stand at the edge of human understanding and peer into the abyss. We are about to embark on a journey through the 25 most perplexing astronomical phenomena still unexplained by science. These are the cosmic head-scratchers that keep astrophysicists awake at night, the observations that stubbornly refuse to fit into our neat models of the universe. From signals that hint at intelligence we cannot comprehend to celestial objects that behave as if they are breaking the laws of physics, each one represents a frontier, a challenge to our curiosity and a testament to how much we have yet to learn. This is not a catalogue of failures, but a celebration of the beautiful, terrifying, and wondrous puzzles that make the cosmos the ultimate frontier of discovery. Prepare to have your perception of reality stretched and your sense of wonder reignited. We will voyage to the edges of distant galaxies, delve into the nature of time and space itself, and confront mysteries that are as ancient as the stars yet as immediate as the latest data from our most powerful telescopes. This exploration is about more than just facts and figures. It is about the fundamental human drive to understand our place in the universe. So, get comfortable, open your mind, and join us as we count down the top 25 astronomical phenomena that science, for now, simply cannot explain. Our journey into the unknown begins not in the distant reaches of space, but in the quiet halls of an observatory in Ohio, with a piece of paper that forever changed our search for cosmic company. In the late summer of 1977, the Big Ear radio telescope at Ohio State University was engaged in a systematic sweep of the heavens, listening for any sign of intelligent life beyond Earth. For the most part, its recordings were a predictable cacophony of background static and natural cosmic noise. But on the night of August 15th, something extraordinary happened. For exactly 72 seconds, the telescope's receiver locked onto a signal so powerful and so peculiar that it defied all conventional explanation. It was a burst of intense, narrowband radio waves, concentrated at a frequency near 1420 MHz, a frequency that happens to be within a protected band of the spectrum where earthly transmissions are forbidden, a quiet channel ideally suited for listening for whispers from the stars. The data from that night was printed out on continuous feed paper, and a few days later, astronomer Jerry Amon was reviewing the alphanumeric printouts, where signal strength was represented by numbers and letters. As his eyes scanned the page, he saw a column of data that made him stop dead. There, amidst a sea of empty space and low-level noise, was the sequence 6 equals UQQJ0. The signal strength was so far off the charts that it was represented by the number 6 and the letter U, the highest value on the printout. Amon was so stunned by the sheer intensity and perfect profile of the signal that he circled the alphanumeric string in red pen and in the margin simply wrote, "Wow." This single, heartfelt annotation gave the signal its now legendary name. What made the WOW signal so compelling was its precise fingerprint, which matched exactly what scientists had predicted for an artificial interstellar transmission. It was narrowband, meaning all its power was focused into a very specific frequency, unlike the broad-spectrum emissions of natural cosmic objects like pulsars or quasars. It also exhibited a clear intensity curve, rising and then falling over the 72-second window, which is exactly what you would expect as the slowly rotating Big Ear telescope focused its beam on a fixed point in the sky, moved directly over it, and then passed by. This perfect signal profile pointed to a source located in the constellation Sagittarius, a region dense with stars, yet no known astronomical object resides at that specific spot. The immediate and obvious question was, could it be repeated? If this was a genuine beacon from another civilization, it should be detectable again. And so began decades of dedicated searches using increasingly sophisticated equipment aimed at that same patch of sky. Yet, in the over 40 years since that summer night, not a single whisper, not even a hint of a similar signal, has ever been detected again. The WOW signal remains a solitary, brilliant flash in the cosmic dark. This profound silence is a core part of the mystery. If it was a deliberate broadcast, why was it only sent once? If it was an accidental leakage from an alien civilization, like our own television and radio signals leaking into space, why have we never detected anything like it since? Scientists have, of course, proposed natural explanations. One of the most discussed theories suggested that the signal could have been caused by a cloud of hydrogen gas surrounding a passing comet. The idea was that comets release large amounts of hydrogen, which can emit radio waves at around the 1420 MHz frequency. However, this explanation has significant flaws. Detailed analysis later showed that no known comets were in that precise area of the sky on that specific date. Furthermore, the hydrogen cloud of a comet is diffuse and spread out, making it highly unlikely to produce such an intensely focused and narrowband signal that perfectly mimicked an artificial transmission. Most astronomers consider the comet explanation to be an unsatisfying stretch, an attempt to fit a square peg into a round hole using a hypothetical that doesn't quite match the observed data. So we are left with an enduring cosmic riddle. The signal had all the hallmarks of intelligence, yet it vanished without a trace. Natural explanations feel inadequate, while the extraordinary possibility of an extraterrestrial origin remains just that, a possibility, tantalizing and unproven. The WOW signal stands as a perfect example of a mystery that is both simple in its facts and profound in its implications. It is a single data point that challenges our place in the universe, a one-time event that continues to echo through the decades, reminding us that we may have, just once, heard a voice from the darkness, only for it to be swallowed by the silence before we could answer. From a single, fleeting signal that may or may not have been a cosmic hello, we now turn our attention to a ghost that permeates every corner of the cosmos, an invisible presence so vast it dictates the very fate of the universe. If you were to make a complete inventory of everything that exists, every star, every planet, every speck of interstellar dust, and even every one of us, you would have accounted for a mere 5% of reality. The rest is a profound and humbling mystery, beginning with a substance we know must exist, but have never directly seen: dark matter. The story of dark matter begins not in the distant reaches of space, but with the careful observations of a brilliant and determined astronomer named Vera Rubin in the 1970s. She was studying the rotation of spiral galaxies, expecting to confirm a straightforward principle of physics. Just as planets in our solar system move more slowly the farther they are from the Sun, Pluto orbits much more sluggishly than Mercury. Stars on the outer edges of a galaxy should orbit much more slowly than those near the bright, dense center. But Rubin's data revealed something astonishingly different. The stars at the fringes of galaxies were whipping around at nearly the same high speed as those close in. It was as if the entire galaxy was rotating like a solid plate, a behavior that defied the laws of gravity as we understood them. The only plausible explanation was that each galaxy was surrounded by an enormous, invisible halo of something, a substance that was not emitting or absorbing light, but was exerting an immense gravitational pull, holding the galaxy together and speeding up its outer stars. This something was dark matter. This galactic evidence was just the beginning. Another powerful line of proof comes from a phenomenon predicted by Einstein's theory of general relativity, gravitational lensing. Massive objects warp the fabric of space-time around them, bending the path of light that travels past them, much like a glass lens bends light. Astronomers can observe this when they see distant galaxies whose light is distorted into strange arcs and rings by the gravity of a massive galaxy cluster in the foreground. But here's the catch: the visible mass of the foreground cluster is never enough to account for the extreme bending of the light. There must be a tremendous amount of unseen mass, a scaffold of dark matter, enveloping the cluster and creating this cosmic mirage. Perhaps the most compelling evidence for dark matter's dominance comes from the afterglow of the Big Bang itself, the cosmic microwave background. This faint radiation which fills all of space is a snapshot of the infant universe. The precise patterns of hot and cold spots in this radiation reveal the universe's initial conditions. The patterns we observe are perfectly consistent with a model of the universe where dark matter makes up about 27% of the cosmic budget. Without dark matter's gravitational influence in those first moments, the ordinary matter we see today would never have been able to clump together to form the galaxies and vast cosmic structures that define our night sky. So, what is this mysterious substance? The leading hypothesis is that it is a new type of elementary particle, one that barely interacts with normal matter except through gravity. Primary candidates have names that sound like they're from science fiction. There are WIMP, or weakly interacting massive particles, which are theoretical heavy particles that could be relics from the Big Bang. Then there are actions, hypothetical ultra-lightweight particles that could flow through the universe like a ghostly wave. For decades, physicists have been building exquisitely sensitive experiments deep underground to shield them from cosmic rays, hoping to catch a WIMP bumping into a nucleus of normal matter. Others are constructing powerful magnetic fields to try and convert actions into detectable photons. So far, despite these monumental efforts, every detector has come up empty. Dark matter remains stubbornly, utterly elusive. This is the essence of the puzzle. We see its shadow everywhere. We can map its distribution across the universe with incredible precision. We know it is the hidden architect of the cosmos, the framework upon which the visible universe is built. Yet, after decades of searching, we have no idea what it actually is. It is a fundamental constituent of reality that is completely invisible to us, a reminder that the universe is far stranger and more mysterious than it appears. If dark matter is the invisible scaffold holding the cosmos together, then its cosmic counterpart, dark energy, is the mysterious force determined to tear it all apart, and its discovery was even more shocking. For most of the 20th century, astronomers were locked in a debate about the ultimate fate of the universe. Would the gravitational pull from all the matter in the cosmos eventually halt its expansion from the Big Bang, leading to a big crunch, or would it continue to fly apart forever, slowly cooling into a dark and frozen eternity? The general assumption was that gravity, acting as a cosmic brake, would be slowing the expansion down. The only question was by how much. Then, in the late 1990s, two independent teams of astronomers set out to measure this deceleration by observing a very specific kind of stellar explosion, and what they found turned cosmology completely upside down. These researchers were using Type 1, a supernova, which are among the most powerful events in the universe. What makes these supernovas so valuable is that they are standard candles. Each one erupts with a very consistent known peak brightness. This consistency is a gift to astronomers because by measuring how bright the supernova appears from Earth and comparing it to its known intrinsic brightness, they can calculate its distance with remarkable accuracy. Furthermore, by analyzing the redshift of the supernova's light, how much its light waves have been stretched as the universe expands, they can determine how fast the universe was expanding when the star exploded. By looking at extremely distant supernova, they were effectively looking back in time, mapping the expansion history of the universe over billions of years. The results, announced almost simultaneously by the two teams, were not just surprising, they were paradigm-shattering. Instead of finding that the expansion was slowing down, the data revealed that it was speeding up. The most distant supernova were fainter than expected, meaning they were farther away than our models predicted. The universe wasn't just expanding, it was accelerating apart, as if some mysterious, repulsive force was overpowering the collective gravity of all the matter in the cosmos. The lead researchers, Saul Perlmutter, Brian Schmidt, and Adam Rees, would later share the 2011 Nobel Prize in Physics for this monumental discovery, which pointed to the existence of what we now call dark energy. So what is this enigmatic force? In many ways, dark energy is an even deeper mystery than dark matter. We can see the gravitational effects of dark matter on individual galaxies and clusters, but dark energy reveals itself only on the very largest scales as a property of space itself. The leading and simplest explanation is that dark energy is the manifestation of the cosmological constant, an idea first proposed by Albert Einstein and then famously discarded. When Einstein was developing his theory of general relativity, he found that his equations suggested the universe should be either expanding or contracting. Believing at the time in a static, unchanging universe, he introduced a fudge factor, a repulsive force embedded in the fabric of empty space that would counterbalance gravity and keep the universe stable. He later called this his greatest blunder when Edwin Hubble discovered the universe was indeed expanding. Yet, ironically, modern observations suggest Einstein may have been right for the wrong reason. The cosmological constant appears to be real, not as a stabilizer, but as the driver of cosmic acceleration. The implications of this are staggering. Measurements from the cosmic microwave background and other sources now tell us that dark energy constitutes about 68% of the total energy density of the universe. Think about that for a moment. The stars, planets, gas, and dust, everything we can see and touch accounts for about 5%. Dark matter, the invisible glue, makes up about 27%. But dark energy, this mysterious repulsive force, is the dominant component of reality. It is the primary actor in the cosmic play, and we have almost no idea what it is. The simplest version, the cosmological constant, treats it as the innate energy of the vacuum of space. But when physicists try to calculate how strong this vacuum energy should be using quantum mechanics, their predictions are off by a factor of 10 to the power of 120. This is arguably the worst theoretical prediction in the history of science, a number so unimaginably large it highlights a fundamental gap in our understanding of physics. This mystery dictates the ultimate fate of everything. If dark energy remains constant, as the cosmological constant suggests, the acceleration will continue unabated. In a distant future, galaxies beyond our local group will be pushed away from us so fast that their light will never be able to reach us. The universe will become a vast, dark, and lonely place, with island galaxies isolated in an ever-growing void. But what if dark energy isn't constant? Some theories suggest it could grow stronger over time, leading to a terrifying scenario known as the Big Rip, where the repulsive force eventually becomes so powerful that it tears apart galaxies, solar systems, planets, and even atoms themselves. Dark energy is not just a curiosity, it is the force that holds the answer to the final chapter of the universe, a chapter we are only just beginning to read. While dark energy describes a force pushing the cosmos apart on the grandest of scales, one of the most intriguing mysteries in modern astronomy was discovered much closer to home, originating from a tiny, persistent drift in the paths of two human-made objects leaving our solar system. For decades, as the Pioneer 10 and 11 spacecraft journeyed beyond the orbits of the outer planets, scientists at NASA, a jet propulsion laboratory, were meticulously tracking their positions using the faint whispers of their radio signals. These probes were humanity's first ambassadors to the stars, and every bit of data from them was precious. But as the years turned into decades, a subtle and utterly unexpected pattern emerged in the tracking data. Both spacecraft were experiencing a constant, minuscule but undeniable deceleration, a tiny pull back toward the sun that simply should not have been there. This deviation, which became known as the Pioneer anomaly, was astonishingly small, roughly 10 billion times weaker than the gravity we feel on Earth's surface. To put it in perspective, it was equivalent to the gravitational pull you would feel from a single grain of sand held about 2 miles away. In everyday terms, it was negligible. But in the precise, unforgiving realm of orbital mechanics, where trajectories are calculated with phenomenal accuracy over billions of miles, this tiny effect was a glaring red flag. It was as if the solar system itself was whispering a secret that our textbooks on gravity had failed to capture. For over a decade, this anomaly stubbornly persisted in the data, a constant background hum of something unexplained, challenging physicists to find its source. The immediate and most logical assumption was that the cause was coming from the spacecraft themselves. After all, Pioneer 10 and 11 were complex machines, generating heat from their radioactive power sources and emitting that heat into space. If this heat radiation was not perfectly symmetrical, if, for example, more heat was reflected off the back of the spacecraft's main antenna dish than from the front, it could act like a tiny, unintended photon rocket, gently pushing the craft backward. This became the leading hypothesis, and scientists embarked on a monumental forensic effort, creating incredibly detailed computer models of the probe's thermal properties, plumbing systems, and even the electrical wiring, trying to account for every last watt of energy. For years, this thermal explanation seemed the most likely culprit, a testament to the difficulty of accounting for every variable in a decades-long, deep space experiment. However, the mystery refused to die easily. The thermal models were complex, and some researchers argued that the predicted effect from heat radiation didn't perfectly match the observed deceleration. This opened the door to more exotic possibilities that captured the public imagination. Could this be the first hint of a flaw in Einstein's theory of general relativity? Perhaps gravity behaved slightly differently at the very edge of the solar system, or maybe there was a previously unknown form of matter or energy exerting a drag force. Some even speculated about the influence of dark matter, though the density required in our solar neighborhood made that seem unlikely. The Pioneer anomaly became a fertile ground for theoretical physicists, a puzzle that, if solved, might lead to a revolution in our understanding of the fundamental forces. The case was finally largely closed, though not without some lingering questions, thanks to a remarkable feat of scientific detective work. A dedicated team spent years recovering old data tapes and telemetry records, some of which had been stored in basements and even a woman's garage. They painstakingly reconstructed the entire thermal history of the Pioneer probes, accounting for how their heat output changed as their radioactive power sources decayed over time. Their conclusion, published in 2012, was that the anomalous acceleration could indeed be explained almost entirely by the asymmetric radiation of heat from the spacecraft systems. The gentle push of photons slowly leaking from the craft was enough to account for the drift, yet for some, a shadow of a doubt remains. While the thermal explanation is widely accepted as the most probable cause, a few researchers point out that the match is not 100% perfect. There is a tiny residual anomaly, a minuscule fraction of the original signal, that the thermal models don't fully account for. It's a whisper within a whisper. This leaves a tantalizing, albeit slim, possibility that the Pioneer probes may have still encountered something unexpected on their journey into the void. It serves as a powerful reminder of the challenges of deep space exploration, and the incredible precision required to understand the laws of physics governing our cosmic neighborhood. The story of the Pioneer anomaly is a testament to scientific rigor, a decades-long pursuit to explain a tiny deviation, proving that sometimes the biggest mysteries are not found in distant galaxies, but in the painstaking details of our own celestial backyard. As we move from mysteries within our solar system to the greater galactic expanse, we encounter a star so bizarre that it single-handedly revived public speculation about intelligent life in the universe. Designated KIC 8462852, but now universally known as Tabby's star after the astronomer Tabby, who led its initial investigation, this unassuming point of light in the constellation Cygnus became the most mysterious star in our galaxy thanks to data from NASA Kepler Space Telescope. Kepler's mission was to find planets by watching for the telltale periodic dimming that occurs when an alien world passes in front of its host star. These transits are typically tiny, predictable dips in brightness, usually less than 1%, but the data from Tabby's star was unlike anything anyone had ever seen. The star's light curve was chaotic and inexplicable. Instead of the gentle, repeating dips of a planet, Kepler recorded dramatic, irregular plummeting of the star's light. On one occasion, the star's brightness dropped by an astonishing 22%. To grasp how immense that is, consider that if Jupiter, the largest planet in our solar system, were to transit the Sun, it would cause a dimming of only about 1%. A 22% drop implies an object or a collection of objects blocking nearly a quarter of the star's light, something on a scale far beyond any single planet. Even more baffling was the pattern, or more accurately, the lack of one. The dips were not periodic. They occurred at random intervals, sometimes lasting for days, other times for weeks, with no discernible rhythm. It was as if something was intermittently and massively obscuring the star in a way that defied all conventional astronomical models. Faced with such an unprecedented signal, astronomers did what they do best: they proposed hypotheses. The initial and most conservative explanation involved a vast swarm of comets. The idea was that a family of exocomets, perhaps disturbed by a passing star, could have been drawn in towards Tabby's star, vaporizing and creating enormous clouds of dust and debris that would cause the observed irregular dimming. While this could theoretically account for the aperiodic nature of the dips, the explanation has significant problems. To block 22% of the star's light, you would need an absolutely immense number of comets, far more than we observe in our own solar system, and it's unclear what could have triggered such a catastrophic event. Furthermore, follow-up observations in the infrared failed to detect the excess heat that such a massive dust cloud should have produced. The inability of the comet swarm model to fully explain the data opened the door to more exotic possibilities, including the one that captured the world's imagination: the alien megastructure hypothesis. This idea, most famously proposed by astronomer Jason Wright, suggested that the irregular dimming could be consistent with a vast, partially constructed Dyson sphere, a hypothetical structure an advanced civilization might build to capture a significant portion of its star's energy. Such a megastructure, composed of orbiting panels or habitats, would not be a perfect sphere and would therefore cause irregular, deep dimming as it rotated around the star, much like the observed light curve. It was a thrilling, if highly speculative, idea that highlighted just how strange the data truly was. Importantly, scientists like Wright presented it not as a likely conclusion, but as a last resort hypothesis to be tested and ideally ruled out. Subsequent observations have only deepened the mystery. In 2017, the star underwent a major series of dimming events, allowing astronomers from around the world to train a multitude of telescopes on it. Crucially, they found that the dimming was much more pronounced in blue light than in red light. This chromatic effect is a classic signature of dust. Small dust particles scatter blue light more effectively than red, so when they pass in front of a star, they make the star appear redder as it dims. This finding makes the pure, solid structure alien megastructure idea much less likely, as a solid object would block all wavelengths of light equally. However, it doesn't simply return us to the simple comet swarm answer. The dust around Tabby's star is unusual. It seems to be made of very fine particles, and the precise way the dimming occurs suggests a complex and clumpy distribution that is still not fully understood. So, where does that leave us? The current leading theory is that Tabby's star is surrounded by a circumstellar dust cloud of unknown origin. It could be the result of a recent planetary collision, a monstrously large version of the asteroid belt in our solar system, or the aftermath of a moon being torn apart by the star's gravity. Yet, each of these natural explanations struggles to account for the full range of the star's bizarre behavior over time. The mystery of Tabby's star is a perfect case study in modern astronomy. It demonstrates how an anomaly in big data can lead to a rigorous scientific process that carefully weighs mundane explanations against extraordinary ones. While the alien megastructure idea has largely faded from prominence, it served a vital purpose. It ignited public interest and showed that we are now capable of detecting phenomena so strange they challenge the very limits of our imagination. Tabby's star remains an unsolved puzzle, a testament to the fact that our galaxy still holds wonders we are only beginning to comprehend. Now, we journey from the strange, long-term dimming of a single star to events of almost unimaginable brevity and power, flashes in the cosmic dark that appear and vanish in the blink of an eye. Imagine all the energy our sun releases over the course of nearly a century. Now, imagine that same titanic amount of energy being unleashed not over decades, but in a single millisecond, a thousandth of a second. This is the staggering scale of a fast radio burst, or FRB. These are not gentle signals or slow cosmic processes. They are the universe's most intense and mysterious fireworks, and for years their very existence was doubted. The story of FRBs begins not with a triumphant announcement, but with a puzzle hiding in plain sight. In 2007, a young astronomer named Duncan Lorimer was poring over archival data from the Parkes radio telescope in Australia, recorded 6 years earlier. He was searching for new pulsars, the rapidly spinning corpses of dead stars, but buried in the data from a single day in 2001 was something that didn't fit any known pattern. A blast of radio waves so powerful it saturated the telescope's receiver, a burst that lasted just 5 milliseconds. It had come from deep intergalactic space, and its signal displayed a telltale sign called dispersion, where lower frequency radio waves arrived slightly later than higher frequencies, indicating it had traveled through a vast amount of cosmic plasma. This single event, now known as the Lorimer burst, was so energetic and so brief that many in the astronomical community were skeptical, wondering if it was just a glitch, an instrument error, or perhaps a signal from a terrestrial source like a microwave oven on the observatory grounds. The mystery deepened over the following years as more of these bursts were discovered, first at Parkes and then at other radio telescopes around the world. With each new detection, it became undeniable that FRBs were a genuine astrophysical phenomenon, not some local quirk, but their fleeting nature made them incredibly difficult to study. Catching one was like trying to photograph a lightning strike with a camera that only takes one picture a day. The breakthrough came in 2016 when astronomers made a landmark discovery. They found an FRB that repeated. Unlike the one-off bursts that flashed once and were never seen again, this source, designated FRB 121102, sent out multiple bursts over time. This single finding ruled out cataclysmic, one-time events as the sole explanation and opened the door to studying the environments that produce these explosions. So, what cosmic engine could possibly generate such staggering amounts of energy in such an infinitesimally short time? The list of suspects is as fascinating as it is varied. One of the leading candidates is a type of neutron star called a magnetar. These are the universe's ultimate magnets, stellar remnants with magnetic fields so powerful they could erase a credit card from halfway to the moon. A starquake on the surface of a magnetar, a sudden cracking of its incredibly dense crust could, in theory, release a colossal amount of magnetic energy, creating a flash of radio waves that we would observe as an FRB. In a dramatic confirmation of this idea, in 2020, astronomers detected an extremely bright FRB coming from within our own galaxy, and it was traced directly to a known magnetar. This was a huge step forward, strongly suggesting that at least some FRBs are born from these magnetic monsters. But the story is far from simple. While magnetars might explain some bursts, especially the weaker ones from within our galaxy, the most powerful FRBs coming from billions of light years away may require an even more extreme origin. Theorists have proposed spectacular events like the collision and merger of two neutron stars, or the evaporation of a black hole through Hawking radiation. Some have even ventured into more speculative territory, suggesting possibilities like cosmic strings, theoretical defects in the fabric of space-time, or, inevitably, the distant echoes of advanced civilizations powering interstellar light sails. While the extraterrestrial intelligence idea is the least likely explanation, it underscores just how enigmatic these signals remain. The true power of FRB science, however, lies not just in understanding the bursts themselves, but in using them as tools to explore the invisible cosmos. As an FRB's radio waves race across the universe, they pass through clouds of ionized gas, the diffuse material that floats in the vast spaces between galaxies. This material leaves a subtle fingerprint on the signal, the same dispersion that helped confirm the Lorimer burst's extragalactic origin. By analyzing this dispersion in exquisite detail, astronomers can essentially weigh all the invisible, scattered matter the signal encountered on its billion-year journey. This turns each FRB into a cosmic probe, allowing us to map out the missing ordinary matter in the universe, matter that has been frustratingly difficult to detect by other means. Fast radio bursts, therefore, are a double mystery. They are both profound puzzles in their own right and powerful new instruments for illuminating the dark corners of the cosmos, reminding us that sometimes the most fleeting events can reveal the most enduring secrets. From fleeting cosmic flashes, we now turn to a silence that is, in its own way, even more profound. It is a silence that surrounds a simple, almost childlike question, one that physicist Enrico Fermi reportedly blurted out over lunch with colleagues in the summer of 1950. But where is everybody? This question, now known as the Fermi paradox, is arguably the most haunting and fundamental mystery in our search for cosmic companionship. It confronts us with a glaring contradiction. On one hand, the universe is unimaginably vast and ancient. Our Milky Way galaxy alone contains an estimated 100 to 400 billion stars. Many of these stars are billions of years older than our Sun, and we now know that a significant fraction of them host planets with rocky worlds orbiting in the habitable zone, the region where temperatures could allow for liquid water being incredibly common. Given these staggering numbers and the immense span of cosmic time, it seems statistically inevitable that life should have arisen elsewhere. Furthermore, if even a tiny fraction of that life evolved intelligence and developed technology, the galaxy should have been colonized many times over by now. The universe, by all rights, should be teeming with civilizations, their signals crisscrossing the void, their artifacts perhaps littering our own solar system. And yet, when we train our telescopes on the cosmos, we are met with an eerie, unbroken quiet. The sky is silent, the evidence is absent. This is the paradox, the overwhelming probability of existence set against the complete lack of any observable proof. Scientists and thinkers have proposed a wide spectrum of resolutions to this cosmic conundrum, each with its own unsettling implications. One of the most discussed and most sobering is the concept of the Great Filter. This idea suggests that the evolution of life from its basic origins to a spacefaring, technologically advanced civilization requires passing through a series of incredibly difficult stages. The Great Filter is a hypothetical barrier, a step in this process that is so improbable that it effectively prevents almost all potential life from reaching the galactic stage. The terrifying question is, where is this filter located? Is it behind us, meaning we have already passed through a nearly impossible bottleneck? Perhaps the abiogenesis, the spontaneous emergence of life from non-living chemistry, is an event of such staggering rarity that it has only happened once in our galaxy. Or maybe the jump from simple prokaryotic cells to complex eukaryotic cells, which took over 1 billion years on Earth, is the true barrier. If the filter is behind us, it would mean we are spectacularly lucky, but also profoundly alone. The more chilling possibility is that the Great Filter lies ahead of us. This version of the hypothesis suggests that the development of advanced technology inevitably leads to a civilization's self-destruction. The filter could be the discovery of nuclear weapons, the unleashing of engineered pandemics, the creation of a runaway artificial intelligence, or the catastrophic collapse of an ecosystem. In this scenario, the silence of the cosmos is a grim warning. The reason we see no other civilizations is because they all, without exception, reach a point where their technological prowess outstrips their wisdom and they perish. If this is true, then the filter is not a relic of our past, but a specter in our future, a challenge we have yet to face and may not survive. Other resolutions to the paradox are less apocalyptic but no less mind-bending. Perhaps we are simply the first. The universe may now be ripe for life, but for billions of years it was a hostile place, plagued by frequent gamma-ray bursts and galaxy-quenching supernova that sterilized entire regions. We could be among the very first generation of intelligent beings to emerge in a cosmos that has only recently become calm enough for complex life to flourish. Alternatively, the solution might lie in the sheer scale of space and time. The galaxy is enormous, and the span of a technological civilization might be vanishingly short compared to the age of the galaxy. It's possible that advanced civilizations are, or were, out there, but their signals and their eras of expansion simply did not overlap with our brief window of existence. We might be like an isolated island tribe, unaware that great empires have risen and fallen on continents too distant for us to ever know. Then there are the truly exotic possibilities. Intelligent life might be common, but it has evolved in forms and technologies so alien to our own that we simply do not recognize it. Their means of communication might not be radio waves, but something we haven't even thought to look for, like modulated neutrinos or gravitational waves. They might have transcended biological existence, becoming post-biological intelligences living in simulated realities, or as pure information within Chinese letter of deep space, having no interest in physical expansion or communication with primitive species like us. Another idea is the zoo hypothesis, which suggests that advanced civilizations are aware of us but have chosen to isolate us in a kind of cosmic wilderness preserve, allowing humanity to develop naturally without interference until we reach a certain level of maturity. The Fermi paradox forces us to confront not just the possibility of other life, but the nature of life, intelligence, and technology itself. It holds up a mirror to humanity, asking us which future we will choose. Will we become a filter statistic, a silent warning for some other emerging species? Or will we somehow find a way to navigate the challenges ahead and add our voice to the cosmic conversation, finally breaking the great silence? This notion of a fundamental, guiding structure in the cosmos finds one of its most perplexing expressions in a discovery so unsettling that astronomers gave it a dramatic name: the axis of evil. To understand why this finding is so controversial, we need to revisit the cornerstone of modern cosmology, the cosmic microwave background, or CMB. This faint, all-sky glow is the cooled remnant of the Big Bang's fiery aftermath, a snapshot of the universe when it was just 380,000 years old. For decades, the CMB has been our most powerful piece of evidence for the standard model of cosmology, which includes the Big Bang and the existence of dark matter and dark energy. A key assumption of this model is that the universe is isotropic and homogeneous on the largest scales. In simpler terms, this means the cosmos should have no preferred direction. It should look roughly the same in every direction you gaze, with no special center or edge. The early maps of the CMB from the COBE satellite in the 1990s seemed to beautifully confirm this, showing a remarkably uniform sea of microwaves with only tiny, random variations in temperature, the seeds that would one day grow into galaxies and clusters. But as our technology improved, so did our ability to see finer details. When NASA Wilkinson Microwave Anisotropy Probe, or WMAP, produced its high-resolution, full-sky map of the CMB in the early 2000s, scientists began to scrutinize these tiny temperature fluctuations with incredible precision. They weren't just looking for the randomness they expected, they were also checking for patterns, for any hint of a preferred direction that might challenge the foundational principle of isotropy. What they found, to their profound surprise, was a series of large-scale correlations that seemed to defy the odds. The most temperature variations, the hot and cold spots that represent the universe's earliest structures, appeared to be aligned in a specific way. Even more bizarrely, this alignment, this apparent preferred plane in the cosmos, seemed to correlate with the ecliptic plane of our own solar system, the flat disk in which Earth and the other planets orbit the Sun. The immediate and most logical reaction within the scientific community was to suspect a systematic error. After all, what are the chances that the fundamental structure of the entire observable universe just happens to line up with the arbitrary orientation of our little corner of the galaxy? It would be like drawing a map of the entire Earth and discovering that all the continents are subtly aligned with the floor plan of your own house. The implication is staggering, and most physicists consider it highly unlikely. The leading hypothesis was that the alignment was not a feature of the universe itself, but an artifact of how we observe it. Perhaps there was some unknown contamination from within our solar system, maybe dust or emissions from the Kuiper belt that the WMAP satellite wasn't fully accounting for. Maybe the issue was with the satellite's complex data processing and the methods used to subtract the foreground glow of our own Milky Way galaxy to reveal the pristine CMB beneath. For years, astronomers have painstakingly searched for this kind of error, but frustratingly, no one has been able to definitively identify a source of contamination that fully explains the alignment. This leaves cosmologists in a deeply uncomfortable position. If the axis of evil is not an error, its implications are profound. It could suggest that the universe has a large-scale structure or a preferred direction on scales even larger than what we can observe, a concept that directly challenges the cosmological principle. Some speculative theories have been proposed to account for such a feature. One idea involves cosmic topology, the possibility that the universe is not infinite and flat, but has a finite, complex shape like a hall of mirrors. If the universe was shaped like a giant donut, for example, light could wrap around it, creating correlations and patterns on the sky that would appear as strange alignments. Another, even more mind-bending possibility is that the anomaly is a hint that our universe collided with another, bubble universe during a period of cosmic inflation, an event that would have left an imprint on the fabric of space-time itself. Yet, the majority of scientists remain cautious, leaning on Occam's razor, the principle that the simplest explanation is usually the correct one. They argue that the most probable answer is that the axis of evil is a statistical fluke, a coincidence that appears significant because we are looking for patterns, or that it stems from a subtle, still unknown systematic effect. However, the anomaly has proven stubbornly persistent. Even data from the more advanced Planck satellite, which mapped the CMB with even greater sensitivity, continued to show hints of this strange alignment, though with less statistical significance. The axis of evil, therefore, remains in a kind of scientific limbo, not strong enough to overthrow our standard model of the universe, but too persistent to be comfortably ignored. It serves as a nagging reminder that our view of the cosmos is still imperfect, and that the universe may yet hold surprises about its fundamental nature that we are only beginning to glimpse. Leaving behind the unsettling implications of a possible cosmic axis, we encounter a force that is far more tangible in its influence, a relentless tug that has set our entire galaxy and everything around us on a mysterious course. For decades, astronomers have known that our Milky Way is not simply floating motionless in the void. It is moving, and moving fast, pulled along by the gravitational currents of the cosmos. But when they measured this motion, they discovered something perplexing. The collective gravitational pull from all the visible galaxies in our immediate neighborhood could not account for the speed and direction of our journey. It was as if we were a raft caught in a powerful, unseen river, being pulled toward something immense lurking just beyond the horizon of our vision. This mysterious source of gravity became known as the Great Attractor. The challenge in solving this mystery is not just one of distance, but of perspective. The direction we are being pulled lies in the constellation Centaurus, which, from our vantage point on Earth, happens to be located directly behind the dense central plane of our own Milky Way galaxy. This region of the sky is called the zone of avoidance. It's not that there's nothing there, it's that our view is completely blocked. The galactic center is packed with billions of stars, immense clouds of cosmic gas, and thick lanes of dust that absorb visible light, creating a brilliant but impenetrable wall that obscures nearly 20% of the extragalactic universe from our traditional telescopes. Trying to see the Great Attractor is like trying to see a distant mountain range through a thick, blinding fog bank that you are standing in the middle of. For a long time, this zone of avoidance meant that the Great Attractor remained a gravitational ghost, its presence inferred but its nature completely hidden. The breakthrough began when astronomers turned from optical light to a different part of the electromagnetic spectrum, radio waves. Radio telescopes can peer through the cosmic dust, allowing us to map the structures hidden behind the Milky Way's bulge. What these observations revealed was not a single, unimaginably massive object, but something perhaps even more fascinating. The Great Attractor appears to be the gravitational heart of our local supercluster, a vast conglomeration of galaxies known as Laniakea, a Hawaiian word meaning immeasurable heaven. Within Laniakea, the Great Attractor is a gravitational watershed, a point toward which every galaxy in our local neighborhood is ultimately flowing. And at the center of this watershed lies the Norma cluster, a massive gathering of galaxies along with the nearby Centaurus cluster. Together, these immense structures create a gravitational well deep enough to pull thousands of galaxies, including our own, toward it. Yet, even this colossal confluence of galaxy clusters may not tell the whole story. Our motion does not stop at the Great Attractor. Measurements show that our entire local supercluster, Laniakea, is itself caught in an even larger and more powerful cosmic current. We are being pulled toward something far more massive and distant, an entity known as the Shapley supercluster, the largest known concentration of mass in our observable universe. This places the Great Attractor in a new light. It may not be the ultimate destination, but rather a major waypoint on a much grander cosmic journey. The pull we feel is a complex combination of the gravity from the Norma and Centaurus clusters relatively nearby, and the overwhelming influence of Shapley much farther away, like being drawn toward a nearby hill that itself sits at the foot of a massive mountain range. So, while the mystery has evolved from a single unknown object to a complex web of large-scale structure, fundamental questions remain. the precise distribution of mass within the zone of avoidance is still not fully mapped. There could be additional, unseen concentrations of dark matter contributing to the pull. The exact interplay between the relatively local Great Attractor and the distant Shapley supercluster is an active area of research, refining our understanding of how gravity sculpts the universe on the very largest scales. The story of the Great Attractor is a powerful lesson in cosmic humility. It reminds us that our place in the universe is not static but dynamic, and that even the motion of our entire galaxy is governed by forces that, for a long time, remained hidden in plain sight, or rather, hidden in the blinding light of our own galactic core. Just as we have begun to map the large-scale currents that guide our galaxy, our own solar system occasionally receives a visitor from those unimaginable distances, a celestial traveler that whispers of the dynamics of interstellar space. In October 2017, astronomers at the University of Hawaii's Pan-STARRS 1 telescope detected a faint point of light moving against the backdrop of stars. At first, it was thought to be just another asteroid or comet from the outer reaches of our own solar system. But as they tracked its path over the following nights, they made a staggering realization: its orbit was not bound to the Sun. This object was not from here. It was the first confirmed interstellar object ever observed, a visitor from another star system. They named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. The initial excitement was soon eclipsed by profound bewilderment as astronomers around the world turned their telescopes toward the visitor. The first major surprise came when they tried to determine its shape. Typically, small solar system bodies like asteroids and comets are more or less spherical or lumpy. But Oumuamua was different. By measuring how its brightness changed dramatically as it tumbled end over end, scientists deduced that it was extraordinarily elongated, with a shape likened to a cigar or a pancake, with estimates suggesting it was up to 10 times longer than it was wide. This was an oddity unlike any object we had seen before. The second surprise was what was missing. As Oumuamua made its close pass by the Sun, scientists watched intently for signs of outgassing, the release of gas and dust that forms the characteristic coma and tail of a comet. Yet, despite being heated by the Sun, Oumuamua showed no visible coma, no tail. It appeared utterly inert, like a dark, silent rock, but the deepest mystery was yet to come. As Oumuamua sped away from the Sun, something inexplicable happened. Its trajectory could not be accounted for by gravity alone. Precise measurements showed it was experiencing a tiny but persistent non-gravitational acceleration. It was being pushed ever so slightly, as if by an unseen force. This is a common occurrence for comets. As the Sun heats their icy surfaces, jets of gas act like miniature thrusters, giving them a push. But Oumuamua had shown no signs of this activity. There was no visible dust or gas to explain the push. This was the heart of the enigma, an object behaving like a comet but looking nothing like one. The scientific community scrambled for explanations. The leading natural hypothesis focused on the possibility of outgassing from exotic ices. Perhaps Oumuamua was composed largely of solid hydrogen or nitrogen ice. These substances could sublimate, turn directly from a solid to a gas under the Sun's heat, providing the necessary thrust without releasing the dusty debris that would create a visible coma. A hydrogen iceberg, in particular, would be virtually invisible to our telescopes and could explain the acceleration. However, this idea has significant challenges. A hydrogen iceberg would begin to evaporate rapidly in the heat of interstellar space long before it reached our solar system, likely not surviving the journey. A nitrogen iceberg, similar to what is found on Pluto, is more resilient, but it's unclear how such a large, pure chunk could be ejected from another star system. It was this combination of strange properties, the unusual shape, the lack of a coma, and the mysterious non-gravitational acceleration, that led to a more sensational, though highly speculative, theory. Astronomer Avi Loeb proposed that Oumuamua's behavior could be consistent with it being a light sail, a thin, artificial object designed to be pushed by the radiation pressure from starlight. In this scenario, the object's flat, pancake-like shape would be ideal for sailing, and the slight extra push could be explained by the pressure of sunlight itself, requiring no outgassing at all. Loeb argued that we should at least consider the possibility that Oumuamua was a piece of advanced technology, perhaps a discarded wreckage or a purposeful probe from an extraterrestrial civilization. This provocative idea sparked intense debate. Mainstream astronomers countered that while the object was strange, invoking an alien spacecraft was a last resort, to be considered only after all natural explanations were exhausted. They pointed out that Oumuamua's light curve, while unusual, was not entirely unique, and that our brief observing window it was already departing when discovered meant we had limited data. We may simply be seeing a new type of natural object, one that is common in other star systems but never before witnessed in our own. Since Oumuamua, a second interstellar object, Comet 2I/Borisov, was discovered, and it behaved exactly like a normal comet, suggesting that interstellar space is filled with a variety of objects, some familiar and some profoundly strange. The legacy of Oumuamua is not a solved mystery, but a catalyst for a new field of astronomy. It is a tantalizing glimpse into the building blocks of other planetary systems, a reminder that our own solar system is not the template for the universe. Its brief passage challenges our categories and forces us to reconsider what is possible. Was it an exotic iceberg, a fragment of a shredded planet, or something even more extraordinary? We may never know for sure, as Oumuamua is now far beyond the reach of our telescopes, speeding silently back into the interstellar dark. But its visit has left an indelible mark, proving that the cosmos is capable of sending us puzzles that defy easy classification and ignite our imagination about what else might be sailing the vast ocean between the stars. Leaving behind the mysteries of interstellar visitors, we turn our attention to a world much closer to home, one that has been a constant companion to humanity throughout history, yet holds a secret from a time long before we walked the Earth. Our moon, with its silent, cratered face, appears as a cold, geologically dead world. It has no atmosphere to speak of and, crucially, no global magnetic field like the one that protects our planet from the solar wind. This makes sense given what we know about planetary magnetism. A global magnetic field is generated by what's called a dynamo effect, a process that requires a liquid, convecting, and electrically conductive core, like the molten iron core at the center of the Earth. The Moon, being only about 1% of Earth's mass, should have cooled and solidified completely billions of years ago, its internal engine shutting down. This is why the discovery made from the rocks brought back by the Apollo astronauts was so utterly shocking. Locked within those ancient lunar samples was the unmistakable signature of a magnetic field that was once not just present but surprisingly powerful. The evidence is literally set in stone. When certain types of rock form in the presence of a magnetic field, tiny magnetic minerals within them, like magnetite, align themselves with the direction and strength of that field, freezing a record of it in time as the rock solidifies. When scientists analyzed the lunar basalt rocks that formed from lava flows on the Moon between about 3.2 and 4 billion years ago, they found this precise magnetic record. The data indicated that the Moon once possessed a magnetic field that was, at its peak, perhaps even stronger than Earth's is today. This presents a profound paradox. How could a small body which lost its internal heat relatively quickly have sustained such a vigorous dynamo for hundreds of millions, if not over 1 billion years? It's like trying to understand how a tiny campfire could have heated an entire valley for a millennium. The scale and duration simply don't match our understanding of the physics. Scientists have proposed several compelling theories to solve this lunar conundrum, each involving a different power source for the ancient dynamo. one of the leading ideas points to the Moon's dramatic early history. The prevailing giant impact theory suggests the Moon was formed from debris ejected after a Mars-sized object collided with the young Earth. This traumatic birth would have left the Moon incredibly hot both inside and out. In its first few 100 million years, the Moon was likely much closer to Earth, and the gravitational pull between the two bodies was far more intense. This proximity could have driven powerful tidal forces, not just on the oceans as we see today, but within the Moon's very mantle and core. The constant flexing and friction from Earth's gravity would have generated immense internal heat, much like kneading dough warms it up, potentially keeping the core molten and stirring it vigorously enough to power a magnetic dynamo. As the Moon gradually migrated to its current orbit, this tidal heating would have diminished, eventually allowing the core to cool and the magnetic field to fade away. Another fascinating theory involves the way the Moon's core may have cooled. On Earth, the solid inner core grows slowly as the planet cools, and the process of crystallization releases light elements into the surrounding liquid outer core, driving convection. It's possible that the Moon's core underwent a similar process billions of years ago. As its iron core began to freeze from the center outwards, the act of crystallization could have provided the necessary buoyancy to churn the remaining liquid metal, powering a dynamo for a significant period. This mechanism could have sustained the magnetic field long after the initial heat from formation and tidal forces had waned. However, models suggest this core crystallization might not have started early enough or been powerful enough to account for the full duration of the magnetic field recorded in the Apollo rocks. Perhaps the most exotic hypothesis involves a temporary but catastrophic event. Some researchers have proposed that large, intense impacts during the late heavy bombardment period around 4 billion years ago could have drastically altered the Moon's rotation. A colossal collision might have set the core spinning at a different rate than the mantle and crust. This differential motion, if violent and sudden enough, could have temporarily stirred the core into generating a strong magnetic field, a kind of planetary jump start. While this could explain periods of intense magnetism, it struggles to account for the field's apparent stability over such a long geological timescale. The mystery of the Moon's magnetic field is more than an academic curiosity. It speaks to the dynamic and surprising history of our closest celestial neighbor. It forces us to reconsider the internal lives of seemingly inert worlds and suggests that the early solar system was a place of far greater energy and complexity than we often assume. The fact that we still lack a definitive explanation despite having physical samples in hand is a humbling reminder that even the most familiar objects in the sky can guard profound secrets about their fiery youth. While many of the mysteries we have explored so far exist on a galactic or cosmic scale, one of the most geometrically perfect enigmas in the solar system has been spinning right above us at the North Pole of the planet Saturn. It is a storm of such precise and breathtaking structure that it seems almost artificial. A giant six-sided hexagon, its sides each longer than the diameter of Earth, etched into the planet's atmosphere. This isn't a temporary cloud formation or an optical illusion. It is a persistent, roaring jet stream that has maintained its stark, angular shape for decades, and possibly for centuries, defying the fundamental principles that govern weather patterns on every other world we know. The story of its discovery begins with the Voyager missions in the early 1980s. As the twin spacecraft flew past the ringed planet, their cameras captured the first fleeting glimpses of this bizarre feature at Saturn's North Pole. But with the limited data and the fact that the northern hemisphere was tilted away from the sun and shrouded in the darkness of its long winter, the full significance of the discovery wasn't immediately clear. It was the arrival of the Cassini spacecraft in 2004 that truly unveiled the hexagon in all its glory. As Saturn's northern hemisphere emerged into sunlight, Cassini's advanced cameras and instruments were able to observe this atmospheric wonder in unprecedented detail. confirming it was not only real but stunningly stable and complex. What makes the hexagon so baffling to planetary scientists is its defiance of basic fluid dynamics. In nature, when fluids or gases rotate, they naturally form circular patterns like hurricanes on Earth or the Great Red Spot on Jupiter, or they descend into turbulent, chaotic swirls. They do not, under any normal circumstances, form perfect, stable polygons with sharp, well-defined corners. The Saturn hexagon is a six-sided jet stream where winds scream at speeds of over 300 miles per hour, yet the overall structure remains locked in place, rotating with a period of about 10 hours and 30 minutes. It's as if a massive, invisible cookie cutter is pressed into the planet's atmosphere, holding the storm in this impossible shape. Scientists have not been without ideas. In laboratory experiments, researchers have managed to create similar polygonal shapes by placing a small cylinder in the center of a spinning tank of liquid and rotating the outer tank at a different speed. Under the right conditions, the shear between the different rotating layers can generate standing waves that manifest as polygons. This suggests that the hexagon could be a giant, stable, standing wave pattern in Saturn's atmosphere, created by differences in wind speed at different latitudes. The theory is compelling, but it runs into a significant problem: scale. The laboratory experiments work beautifully in a small, controlled setting. Translating that physics to a jet stream wider than our entire planet, one that has remained stable across decades of observation, is an entirely different challenge. The energy required and the precise conditions needed to maintain such a structure on a planetary scale are difficult to reconcile with our current models. The mystery only deepens when we consider the third dimension. Cassini's instruments revealed that the hexagon is not just a surface feature. It is a towering structure that plunges hundreds of miles down into Saturn's deep atmosphere. This incredible depth suggests that the phenomenon is rooted in processes far below the cloud tops we can see, perhaps involving the interaction between the atmospheric gases and the planet's hidden interior. Furthermore, within the hexagon's boundaries, Cassini observed smaller, swirling vortices that travel along the hexagon's edges like cars on a cosmic racetrack, and witnessed seasonal changes in its color, shifting from a bluish hue to a more golden tone as the northern summer solstice approached. These dynamics indicate that the hexagon is not a static painting on the sky, but a deeply complex and active weather system whose secrets are locked within the unique physics of a gas giant. So, while we have a plausible laboratory analog, the Saturn hexagon remains one of the most striking unsolved puzzles in our solar system. It is a phenomenon that challenges our understanding of how fluids behave under planetary conditions, a reminder that the giant worlds in our cosmic neighborhood operate by rules we are only beginning to comprehend. It stands as a majestic, rotating testament to the fact that even within our own solar system, nature is capable of creating wonders that defy simple explanation, geometric perfection etched onto a canvas of churning hydrogen and helium. From the elegant geometric storm at Saturn's pole, we now venture to the frozen, dark frontier of our own solar system, where a different kind of mystery lies in wait, not a swirling tempest, but a profound and telling silence. Beyond the orbit of Neptune, stretching out into the cosmic dark, lies the Kuiper Belt, a vast donut-shaped region populated by icy remnants from the solar system's birth. For astronomers, this belt is a cosmic fossil record, a preserved scene from the dawn of our planetary system. We expected this record to be extensive, with the number of objects gradually thinning out the farther you travel from the Sun, like a crowd dispersing slowly from a city center. But what we've found is something far more dramatic and puzzling. Instead of a gentle fade, the data reveals a sudden and precipitous drop, an edge so sharp it has become known as the Kuiper Cliff. This cliff is located at a distance of about 50 astronomical units from the Sun, where 1 astronomical unit is the average distance from Earth to the Sun. Up to that point, the population of Kuiper Belt objects, or KBO, behaves as predicted. we find a rich assortment of icy worlds, including Pluto, Haumea, and Makemake, along with countless smaller bodies. But beyond the 50 mark, the number of detectable objects falls off a cliff. It's not a gradual decline, it's an abrupt termination, as if someone built a celestial wall at the edge of the solar system's construction site. This is deeply contradictory to our leading models of solar system formation. The nebula hypothesis suggests that the protoplanetary disk of gas and dust from which the planets formed should have extended much farther out and faded smoothly. The sudden absence of objects implies that the primordial disk either had a surprisingly sharp outer edge for reasons we don't understand, or that something happened in the distant past to violently clear out that distant region. This glaring discrepancy has led scientists to propose some of the most exciting theories in modern planetary science. The most prominent hypothesis is that the Kuiper Cliff is the gravitational signature of an unseen, massive planet lurking in the extreme outer darkness. This hypothetical world, often referred to as Planet 9, would be several times more massive than Earth and orbiting hundreds of astronomical units from the Sun on a long, elliptical path. The gravitational influence of such a planet could act as a cosmic shepherd. As it travels along its distant orbit, its immense gravity could have sculpted the inner edge of the Kuiper belt, either flinging objects from the region beyond 50 into the inner solar system, or ejecting them from the solar system entirely, leaving behind the stark cliff we observe today. The orbit of this proposed planet would be so vast that a single trip around the Sun could take 10 or 20,000 years, explaining why we haven't spotted it yet in our all-sky surveys. However, the Planet 9 theory is not the only possible explanation. Another compelling idea suggests that the cliff is not a product of a single massive object, but a relic from the solar system's earliest days, when it was still forming within a crowded star cluster. In this scenario, a passing star that came close to our infant sun could have gravitationally stripped away the outer material of our protoplanetary disk, effectively shaving off its outer reaches and creating a sharp edge before the Kuiper belt ever fully formed. This would mean the cliff is a fossilized boundary, a permanent scar from a dramatic close encounter that occurred over 4 billion years ago. Alternatively, the explanation might lie in the complex processes of planet formation itself. It's possible that the conditions in the outer disk led to the rapid formation of a few large objects that efficiently gobbled up all the smaller material in that zone, leaving behind a cleanly swept region, though this still doesn't fully account for the sharpness of the cutoff. The search for a definitive answer continues. Astronomers are meticulously mapping the orbits of the most distant KBOs we can find, looking for subtle orbital alignments that would point unequivocally to the gravitational tug of a massive perturber. Each new discovery of an extreme trans-Neptunian object whose orbit is tilted or clustered with others adds another piece of circumstantial evidence to the Planet 9 case. At the same time, advanced simulations are constantly refining our understanding of how protoplanetary disks evolve, testing whether a natural truncation is possible. The Kuiper Cliff is more than just a curiosity. It is a fundamental challenge to our story of how solar systems are built. Its existence forces us to consider that our cosmic neighborhood may be hiding a giant, unknown world, or that its birth was far more violent and interactive than we ever imagined, a solitary system whose boundaries were shaped by a long-lost stellar sibling. If the Saturn hexagon represents a mystery of form and structure, then the enigma of ultra-diffuse galaxies is one of profound absence and ghostly presence. Imagine a galaxy with the sheer mass of our Milky Way, a titanic collection of hundreds of billions of stars. Now, picture that instead of a brilliant spiral disk stretching across the night sky, this galaxy is so faint, so ethereal, that it was almost missed by our most powerful telescopes. This is the reality of galaxies like Dragonfly 44, a celestial phantom discovered in the Coma cluster. It possesses the gravitational weight of a giant, but its stars are spread so thinly that it emits less than 1% of the light of the Milky Way. It is a ghost galaxy, a vast cosmic shadow that challenges our most fundamental ideas about how galaxies are born and live. The discovery of these ultra-diffuse galaxies was not just a surprise, it was a shock to the system of astronomy. For decades, our understanding was built on a seemingly straightforward correlation. More mass means more stars. Giant elliptical and spiral galaxies have huge amounts of both normal matter and dark matter, while dwarf galaxies have less of both. Dragonfly 44 and its kin broke this rule spectacularly. Observations using the Keck and Gemini telescopes revealed that despite having almost no visible stars, this galaxy has a mass comparable to the Milky Way. The only way to account for this is if it is made almost entirely of dark matter. In fact, calculations suggest that dark matter constitutes over 99% of Dragonfly 44 mass, making it a near-pure dark matter halo, a skeleton of a galaxy with almost no luminous flesh. This turns the standard model of galaxy formation on its head. How could a gravitational well so deep and massive fail to pull in enough gas to form a correspondingly immense number of stars? This mystery has led astronomers to propose two intriguing and very different origin stories for these ghostly giants. The first paints a picture of a failed galaxy. In this scenario, Dragonfly 44 began its life like any other protogalaxy, accumulating a vast halo of dark matter in the early universe, but something went wrong. Perhaps it formed in a region of space that was already devoid of the vast reservoirs of neutral hydrogen gas needed to create stars. Or maybe, if it resides in a dense galaxy cluster, the intense heat of the intergalactic medium, a superheated plasma that fills galaxy clusters, could have prevented the gas from ever cooling down and collapsing to form stars. The galaxy would have been stillborn, a dark matter framework that never ignited with stellar light, remaining a dormant giant for billions of years. The second, and perhaps more dramatic, theory involves the violent process of galactic cannibalism. Galaxy clusters are ruthless environments where the strong gravitationally dominate the weak. Large galaxies often strip smaller ones of their stars and gas through tidal forces, a process that can leave the victim galaxy shredded and faint. The theory suggests that ultra-diffuse galaxies like Dragonfly 44 could be the remnants of such a cosmic feast. A once normal, star-filled galaxy could have had almost all of its stars ripped away during a close encounter with a much larger neighbor. What would remain is the original galaxy's dark matter halo, which is much more difficult to disrupt, along with a mere sprinkling of the original stars that managed to stay gravitationally bound. In this view, Dragonfly 44 is not a failed galaxy, but a galactic ghost, the pale remnant of a system that was devoured, its luminous body consumed and its dark soul left behind. Determining which story is correct is an active and challenging area of research. Astronomers are now searching for subtle clues within these faint galaxies. If they are failed galaxies, they should be ancient systems populated mostly by very old stars. If they are the remnants of cannibalism, their stellar populations might show a more complex history, with evidence of the traumatic interactions that stripped them bare. The environment is another key clue. Finding such galaxies in the relative isolation of the cosmic voids would support the failed galaxy hypothesis, while their prevalence in the crowded, violent environment of galaxy clusters would point strongly to tidal stripping as the primary cause. Each new ultra-diffuse galaxy discovered adds a piece to this puzzle, forcing us to refine our models of galactic evolution and acknowledge that the universe has more than one way to build or unbuild a city of stars. These ghostly giants stand as a testament to the invisible power of dark matter and the dramatic lives of galaxies, reminding us that what we see with our telescopes is only a tiny fraction of the true, massive, and often hidden reality of the cosmos. But this careful mapping of our cosmic neighborhood depends on a fundamental number, a single value that dictates the pace of the entire universe's expansion. This number is the Hubble constant, and for decades, astronomers have strived to pin down its exact value with ever-increasing precision. The expectation was that as our tools and techniques improved, the various methods of measurement would converge on a single, universal truth. Instead, something deeply unsettling has happened. The two most precise methods ever developed have not converged. They have diverged, creating a growing gap that is sending shockwaves through the field of cosmology. This discrepancy is known as the Hubble tension, and it is not just a minor statistical fluke. It is a full-blown crisis that may be pointing toward a fundamental flaw in our understanding of the cosmos. To grasp the gravity of this tension, we need to understand the two very different ways scientists measure the universe's expansion rate. The first method is a cosmic distance ladder, a step-by-step process that builds out from our local universe. It begins with a class of stars called Cepheid variables. These are stars that pulsate with a remarkable regularity. The longer their pulsation period, the higher their true intrinsic brightness. This period luminosity relationship makes them perfect standard candles. By finding Cepheids in nearby galaxies, astronomers can measure their period, know their true brightness, and then calculate the distance to their host galaxy with great accuracy. The next rung on the ladder involves Type Ia supernova, the same celestial explosions that reveal dark energy. These supernovae are even brighter than Cepheids, allowing us to see them in galaxies billions of light-years away. By finding galaxies that contain both a Cepheid variable and a Type Ia supernova, scientists can calibrate the supernova's brightness using the Cepheids' known distance. Once calibrated, these supernovae become powerful probes for measuring distances across the vast expanse of the universe. By comparing these distances to the redshift of the galaxies, how much their light has been stretched by the expansion of space, astronomers can calculate the Hubble constant. This is a direct measurement of the universe's current expansion rate, and it has been refined to an incredible degree of precision by projects like the SH-0ES team using the Hubble Space Telescope. The second method takes a completely different approach. Instead of looking at the universe today, it looks back to its very infancy, to the cosmic microwave background. The CMB is a fossil relic from when the universe was only 380,000 years old, a snapshot of its baby picture. By studying the intricate patterns of hot and cold spots in this radiation with exquisite detail, as done by the Planck satellite, cosmologists can work backwards. They can take our best model of the universe, the lambda cold dark matter model, which includes ordinary matter, dark matter, and dark energy, and run the cosmic film in reverse. They can input the initial conditions seen in the CMB and let the model simulate 13.8 billion years of expansion to predict what the Hubble constant should be today. This is not a direct measurement of the current expansion. It is a prediction based on our understanding of the universe's physics in its first moments. The crisis emerges when we compare the results. The cosmic distance ladder method, our measurement of the present-day universe, gives a Hubble constant of about 73 kilometers per second per megaparsec. This means that for every million parsecs, about 3.26 million light-years, a galaxy is away from us. It appears to be moving away 73 kilometers per second faster. Meanwhile, the primordial CMB method, our inference from the early universe, predicts a slower expansion rate of about 67 kilometers per second per megaparsec. Now, a difference of 6 might not sound like much, but the precision of these measurements is so high that the chance of this discrepancy being a simple error is less than 1 in a million. It is a stubborn, persistent gap that refuses to close, no matter how much the data is reanalyzed or the methods are refined. It's as if you used two different, impeccably accurate clocks to time a race, and one consistently told you the runner was faster than the other. The problem isn't with the clocks, it's with our understanding of the race itself. This Hubble tension is so significant because it suggests a crack in the foundation of our standard model of cosmology. The lambda-CDM model has been spectacularly successful at explaining a vast array of cosmic phenomena, from the distribution of galaxies to the abundance of light elements. But the Hubble tension indicates that the model might be incomplete. Perhaps there is something about the early universe that we are missing. Maybe dark energy, which we assume has been constant, is not constant at all. It could have evolved over time, or it could be a new, dynamic form of energy that changed the expansion history in a way our models don't account for. Other possibilities involve the mysterious neutrino. What if these ghostly particles which flood the universe have properties we haven't yet discovered, such as a slightly different mass or an unexpected interaction with other forms of matter? These could have subtly altered the rate at which cosmic structures formed, leading to the discrepancy we see today. There are even more exotic ideas, such as the existence of a new type of dark radiation in the early universe, or the possibility that dark matter interacts with itself in ways we haven't predicted. Each of these potential solutions would represent a monumental shift in physics, a discovery of new physics beyond our current standard model. The ongoing effort to resolve the Hubble tension is a testament to the scientific process. Astronomers are not simply accepting the discrepancy, they are attacking it from every angle. They are searching for new, independent ways to measure the Hubble constant, using gravitational waves from colliding neutron stars or the subtle flickering of quasars. They are scrutinizing every step of the cosmic distance ladder, checking for hidden systematic errors that could be skewing the local measurement. And theorists are working feverishly to develop tweaked versions of the lambda-CDM model that can accommodate both the early and late universe observations without breaking everything else the model successfully explains. The Hubble tension is more than a technical problem, it is a thrilling frontier. It represents the possibility that we are on the verge of a profound discovery, one that could force us to rewrite the textbooks and deepen our understanding of the fundamental forces that have shaped the cosmos from its first moment to the present day. Just when we think we understand the fundamental particles that make up the universe, the cosmos sends us a reminder that there are projectiles of almost unimaginable power screaming through the void, and we have no idea what is firing them. These are not rays of light or gentle waves of radiation. They are cosmic rays, atomic nuclei stripped of their electrons and accelerated to a staggering fraction of the speed of light. While cosmic rays are a constant drizzle throughout space, a few rare particles carry so much energy that they defy belief. These are ultra-high-energy cosmic rays, and they pack a punch millions of times greater than the most powerful particle accelerators ever built by humans, like the Large Hadron Collider. A single one of these subatomic bullets carries the kinetic energy of a well-thrown baseball, all compressed into a particle smaller than an atom. The forces required to accelerate a proton or an atomic nucleus to such an extreme are almost incomprehensible, pointing to the most violent and energetic engines in the universe. The mystery of these cosmic cannonballs is not just their incredible energy, but the profound difficulty in figuring out where they come from. Imagine standing in the middle of a thunderstorm, trying to figure out which cloud a particular raindrop fell from by looking at the splash it makes on the ground. Now make that raindrop invisible and have it fall through a maze of powerful, shifting winds that constantly change its direction. This is the challenge astronomers face. As these charged particles travel across the cosmos, they encounter the weak but pervasive magnetic fields that thread the space between galaxies. These magnetic fields act like a funhouse of mirrors, bending and twisting the paths of the particles in unpredictable ways. By the time one of these ultra-high-energy rays finally smashes into Earth's atmosphere, its trajectory has been scrambled beyond recognition, erasing any direct pointer back to its source. It's a cosmic detective story where the most crucial piece of evidence, the path of the bullet, has been thoroughly wiped clean. So, what kind of cosmic events could possibly serve as these incredible particle accelerators? Scientists have a short list of suspects, each one a contender for the most extreme phenomenon known to physics. One of the prime candidates is the active galactic nucleus, the supermassive black hole at the heart of a galaxy that is actively feeding on surrounding matter. As vast quantities of gas and dust spiral into the black hole's event horizon, they can generate powerful jets of plasma that shoot out from the poles at nearly the speed of light. These relativistic jets could potentially act as a natural particle accelerator, boosting charged particles to the phenomenal energies we observe. Another potential source is a gamma-ray burst, the most energetic explosion since the Big Bang, thought to result from the collapse of a massive star or the merger of two neutron stars. The sheer, concentrated violence of such an event could easily be capable of launching atomic nuclei on a near-light-speed journey across the universe. Yet, even these spectacular explanations sometimes fall short. For the very highest energy cosmic rays ever detected, some theorists have proposed even more exotic origins, such as the decay of hypothetical super-heavy particles left over from the Big Bang, or defects in the very fabric of space-time known as cosmic strings. The unsettling possibility remains that we may be seeing the signature of a physical process or a celestial object that we have not yet even imagined. To catch these elusive particles, scientists have had to build detectors on a monumental scale. Since these ultra-high-energy cosmic rays are incredibly rare, striking a given square kilometer of Earth only about once per century, you need to watch a vast area of the sky continuously. The most ambitious effort to do this is the Pierre Auger Observatory in Argentina. It's not a single telescope, but an array of over 1,600 water tanks spread across 3,000 square kilometers, an area comparable to the state of Rhode Island. When a cosmic ray slams into the upper atmosphere, it creates a cascade of secondary particles, an extensive air shower that rains down over an area of many square kilometers. The Auger tanks detect the faint flashes of light produced when these secondary particles pass through the water. By timing the arrival of the shower at different tanks, researchers can reconstruct the direction and energy of the original cosmic ray. The observatory also uses fluorescence telescopes to watch the faint ultraviolet light the air shower itself produces as it streaks through the night sky. This two-pronged approach provides a much more detailed picture of each event. Despite decades of data from Auger and other observatories, the puzzle of ultra-high-energy cosmic rays remains frustratingly unsolved. There have been hints of anisotropy, slight statistical overdensities in the directions from which these particles arrive, but no smoking gun pointing to a specific class of objects has been identified. The sources appear to be distributed across the sky, and they are not perfectly aligned with the known locations of active galactic nuclei or gamma-ray burst remnants. This suggests that the accelerators might be relatively common, but that the particles are scrambled so thoroughly by intergalactic magnetic fields that their origins are completely blurred. Or it could mean that the true sources are something else entirely, objects that are too faint or too temporary for our current telescopes to easily spot. The quest to solve this mystery is driving the design of next-generation observatories that will be even larger and more sensitive, hoping to catch enough of these rare events to finally see a pattern emerge from the cosmic noise. These ultra-high-energy particles are more than just a curiosity. They are messengers from the most energetic processes in the universe, carrying encoded information about the forces that shape them. Deciphering their origin is not just about finding a celestial accelerator. It is about probing the absolute limits of physics in the most extreme environments the cosmos has to offer. But if ultra-high-energy cosmic rays represent the extreme of formless, chaotic energy, the cosmos is equally capable of producing structures of breathtaking and seemingly artificial geometry. Far from the violent collisions that may create those subatomic bullets in the quiet, final stages of a star's life, we find one of the most visually perfect and puzzling objects in the heavens, the Red Rectangle Nebula. Located about 2,300 light-years away in the constellation Monoceros, this nebula was given its name by astronomers during the 1970s after its appearance on early photographic plates. And while more modern observations with the Hubble Space Telescope have revealed a structure far more intricate and beautiful than a simple rectangle, the name has stuck, perfectly capturing the object's bizarre, angular defiance of the round, flowing shapes we typically associate with cosmic gas clouds. What Hubble revealed is nothing short of astonishing. Instead of a roughly spherical or irregularly shaped planetary nebula, we see a series of nested, concentric rectangular shells, like a set of cosmic boxes placed inside one another. Emanating from the center of this structure is a prominent, dark ladder of rungs, creating a striking X-shaped symmetry that bisects the glowing red rectangles. The overall impression is less of a natural celestial object and more of an intricate piece of architecture or a spiritual mandala projected onto the sky. This level of geometric precision is profoundly unusual. In the near vacuum of space, where forces act uniformly in all directions, we expect things to be round stars, planets, the bubbles blown by stellar winds. The emergence of such sharp corners and straight lines is a clear signal that a highly specialized and constrained physical process is at work. The secret to this strange shape is believed to lie at the very heart of the nebula in a pair of dying stars. The red rectangle is not the product of a single star, but almost certainly a binary system. At its center is a dying star, similar to our Sun, but in its final throes, which has puffed off its outer layers. This star, however, is not alone. It is locked in a close orbital dance with a companion star. This duo is the cosmic sculptor. As the primary star sheds its atmosphere, the material doesn't simply flow outward in a spherical shell. Instead, it is drawn toward the companion star, forming a thick, dense disk of gas and dust around the binary pair, known as a circumbinary torus. Think of this torus as a donut-shaped belt that tightly confines the outflowing material, preventing it from expanding up and down. This is where the magic happens. The intense radiation and stellar winds from the central stars need an escape route. The path of least resistance is perpendicular to the plane of the dense dust torus. This forces the outflows into two opposing cones or jets shooting out from the poles of the system. From our vantage point on Earth, we are looking almost directly at the side of this torus. We see the two cones extending away from us and toward us, their edges appearing to create the straight sides of the larger rectangle. The nested, concentric rectangles are then thought to be a result of episodic mass loss. The central star didn't shed its skin in one continuous event, but in a series of pulses or fits and starts. Each pulse created a shell of material that was then shaped by the same bipolar outflow, resulting in the layered, box-like appearance we observe. Yet, even this elegant model leaves a crucial aspect unexplained: the perfect X shape and the distinct ladder of dark rungs. The bipolar flow accounts for the overall rectangular outline, but not for the sharp, diagonal spokes that give the nebula its name. One leading theory suggests that the dust in the outflowing gas is incredibly effective at scattering the star's light, but it scatters light more efficiently in specific directions. This anisotropic scattering could potentially enhance the appearance of the cone's edges, creating the diagonal features. The dark rungs are even more puzzling. They may represent waves of denser material within the outflow, or perhaps shadows cast by clumps of dust orbiting within the central torus, periodically blocking the light and creating a series of dark bands. However, the exact hydrodynamic or radiative process that produces such a regular, ladder-like pattern remains a topic of active research and debate. The Red Rectangle Nebula, therefore, stands as a magnificent example of how complex and beautiful cosmic structures can emerge from the interplay of simple physical forces. It shows us that the death of a star, when choreographed by the gravity of a companion, can result in something far more ordered and intricate than a chaotic explosion. It is a natural masterpiece, a temporary sculpture of gas and dust that challenges our intuition and deepens our appreciation for the subtle physics that govern even the final acts of a star's life. Its precise geometry may be elusive, but it serves as a stunning reminder that the universe has a hidden affinity for patterns, waiting to be revealed by a patient and curious gaze. While many stars live out their lives in the stable clusters where they were born, the galaxy has its share of celestial renegades, solitary wanderers blazing a trail through the cosmic dark at speeds that defy imagination. Picture a star like Zeta Ophiuchi, a brilliant blue giant so massive it outweighs our Sun by 20 times. This isn't a star calmly orbiting the galactic center. It is a runaway hurtling through space at nearly 60,000 miles per hour. Its passage is so violent that it creates a spectacular bow shock in the interstellar medium, a cosmic wave of compressed gas and dust that glows in infrared light, resembling a ship's prow cutting through an invisible ocean. This star is on a one-way journey out of its neighborhood, and its incredible speed points to a dramatic and violent past, an ejection event of almost unimaginable force. The primary engine for creating these stellar speedsters is the relentless pull of gravity within the most crowded parts of the galaxy. Imagine a dense young star cluster, a stellar nursery packed with hundreds of hot, newborn stars all orbiting a common center of mass. In this gravitational mosh pit, close encounters are inevitable. When two stars swing past each other, their gravitational fields interact like a slingshot. Often, this is a stable interaction, but in a complex dance involving 3 or more stars, a rare but powerful outcome can occur. A gravitational slingshot that flings one of the stars clear out of the cluster entirely. In this scenario, the star itself remains intact, but it is given a tremendous kick, set on a new, high-velocity trajectory that will carry it across the galaxy, leaving its stellar siblings far behind. This process effectively steals gravitational energy from the cluster and transfers it into the kinetic energy of a single, runaway star. An even more explosive mechanism involves the death of a stellar companion. Many massive stars are born in binary systems, 2 stars locked in a mutual orbit. If the more massive star of the pair reaches the end of its life and explodes as a supernova, the sudden, catastrophic event can launch the surviving star on a wild journey. The physics here are stark and dramatic. In a binary system, the stars orbit around a shared center of mass. When one star explodes, it instantaneously loses a huge fraction of its mass. The stellar core collapses into a neutron star or black hole, while the outer layers are blasted into space. This rapid mass loss catastrophically disrupts the gravitational bond holding the system together. The surviving companion is no longer tethered by the same force and is effectively flung away at its orbital velocity, which can be hundreds of kilometers per second. It's as if you were swinging a ball on a string and the string suddenly snapped. The ball would fly off in a straight line. The runaway star becomes a living testament to a catastrophic death that occurred millions of years ago. The central mystery surrounding stars like Zeta Ophiuchi is not whether they were ejected, but precisely how and from where. Tracing their path back to a point of origin is a monumental challenge that combines the skills of a cosmic detective and an archaeologist. Astronomers can measure the star's current velocity and its direction of travel with great accuracy. They can also estimate its age. The next step is to run the clock backwards, calculating the star's trajectory through the complex gravitational field of the Milky Way, accounting for the pull of spiral arms, giant molecular clouds, and the overall galactic potential. This process of astronomical backtracking is incredibly sensitive. Over the millions of years a runaway star has been traveling. Even the tiniest uncertainties in its initial velocity or the galactic model can lead its projected path to diverge wildly from its true point of origin. It's like trying to trace a single raindrop back to the exact cloud it came from after it has flowed down rivers and over waterfalls for centuries. This challenge is compounded by the fact that the ejection event itself often erases the very evidence needed to confirm it. If a star was ejected by a multi-body gravitational interaction, the cluster it came from will have continued to evolve and drift apart over the intervening eons, making a definitive match difficult. If it was the survivor of a supernova, the telltale remnant, the expanding cloud of debris, and the neutron star or black hole left behind may be faint, distant, and difficult to associate with the runaway star after such a long time. The supernova's own kick would have sent the dead star flying off in its own direction, further separating the two siblings. For many runaway stars, we are left with compelling circumstantial evidence but no smoking gun. We see the star, we understand the physics that could have sent it on its way, but the specific event and location remain tantalizingly out of reach, a ghostly signature of a violent moment lost to deep time. These stellar loners are more than just curiosities. They are probes of the galaxy's dynamic history, their paths encoded with information about the gravitational forces that have shaped the Milky Way, even if the full story of their great escape remains an enduring cosmic cold case. From the violent journeys of runaway stars, we now turn our attention to a much quieter, more subtle mystery, one that is woven into the very fabric of the oldest matter in the universe. It is a problem not of immense scale or bizarre shape, but of a simple, fundamental accounting error. When we look back to the first few minutes of the cosmos, to the fiery forge of the Big Bang itself, our mathematical models perform a near miraculous feat. They predict with stunning accuracy the cosmic abundance of the two lightest elements, hydrogen and helium. The amount of these elements we observe in the most ancient regions of the universe matches the predictions of Big Bang nucleosynthesis almost perfectly. This agreement is a cornerstone of modern cosmology, a triumphant validation of our understanding of the universe's first moments. But there is a third element in this primordial recipe, and for it, the numbers fail dramatically. This is the lithium problem, a small but persistent discrepancy that hints at a crack in our picture of the cosmic dawn. The problem revolves around lithium-7, the stable isotope that makes up over 90% of the natural lithium found on Earth. According to the meticulously refined models of Big Bang nucleosynthesis, the intense heat and density of the first 3 to 20 minutes of the universe should have produced a specific, measurable amount of this isotope. The calculations are precise, taking into account the density of ordinary matter and the rate of nuclear reactions in that primordial soup. Yet, when astronomers measure the lithium abundance in the atmospheres of the most ancient stars in the halo of our galaxy stars, that formed from nearly pristine gas shortly after the Big Bang and have undergone little chemical evolution, they find only about 1/3 of the predicted amount. It is not a small margin of error, it is a factor of 3 discrepancy, a glaring shortfall that has stubbornly resisted explanation for decades. It is as if we had a perfect recipe for a cake, one that correctly predicts the amounts of flour and sugar, but consistently yields only 1/3 of the expected eggs. Scientists have attacked this puzzle from 2 primary angles. The first line of inquiry questions whether our observations are correct. Could we be misunderstanding the data from these ancient stars? Determining the chemical composition of a star is an indirect process. Astronomers analyze the star's spectrum, the rainbow of its light broken down into individual wavelengths. Dark lines in this spectrum correspond to specific elements absorbing light. The strength and shape of these lines are used to calculate abundance. However, this process relies on complex models of stellar atmospheres. If our models of the temperature, pressure, and convection in these old stars are slightly off, we might be misinterpreting the lithium absorption lines, leading to an underestimate. Some researchers have proposed that lithium could be sinking from the thin outer atmospheres of these stars down into their hotter interiors, where it would be destroyed, effectively hiding it from our view. While these are plausible ideas, detailed studies have so far failed to find conclusive evidence that such processes can fully account for the massive, universe-wide lithium deficit. The second and more dramatic possibility is that our understanding of the early universe itself is incomplete. Perhaps the models of Big Bang nucleosynthesis are missing a crucial piece of physics. Could there have been an unknown process in the first few minutes that destroyed lithium as it was forming? One fascinating proposal involves hypothetical particles from the realm of particle physics beyond the standard model. For instance, certain types of dark matter particles could have been present and interacting with normal matter during those initial moments. If these particles decayed or annihilated, they would have injected extra energy into the primordial plasma, altering the delicate balance of nuclear reactions and potentially leading to the destruction of lithium-7. Another idea suggests that magnetic monopoles, hypothetical particles with a single magnetic pole, could have catalyzed nuclear reactions that consumed lithium. These are thrilling possibilities because they connect a small, specific cosmological problem to the search for new, fundamental physics. Solving the lithium problem could, in theory, open a window into the particle nature of dark matter or other exotic components of the cosmos. Yet, after decades of rigorous investigation, the lithium problem endures. Neither adjustments to stellar astrophysics nor introductions of new particle physics have provided a universally accepted solution. This persistence is what makes it so significant. It is not a minor quirk, it is a fundamental mismatch between a key prediction of our most successful cosmological theory and the empirical evidence provided by some of the oldest objects in the galaxy. It serves as a humble reminder that even our most well-tested models of the universe's origin may still be missing a vital ingredient. The lithium problem is a quiet whisper from the dawn of time, a small but unignorable signal that our journey to understand the Big Bang is not yet complete, and that the first few minutes of creation may hold secrets more complex than we ever imagined. While many of the cosmos's wonders require powerful telescopes to observe, one of its most subtle and beautiful mysteries is visible to the naked eye under the right conditions, a gentle pyramid of light that reaches up from the horizon into the heart of the night. Long after the last colors of sunset have faded from the western sky, or just before the first hints of dawn begin to brighten the east, a faint, ethereal glow can sometimes be seen stretching along the path of the ecliptic, the same plane in which the planets orbit our sun. This is the zodiacal light, a soft illumination often described as a false dawn or an otherworldly pillar. For centuries, it was a source of folklore and wonder. We now understand it to be sunlight, scattered by billions upon billions of tiny dust particles that form a vast, lens-shaped cloud permeating the inner solar system. But knowing what it is has only led to a deeper puzzle. Where does all this dust actually come from, and why does there seem to be more of it than our best models can explain? The primary suspects in this cosmic dusting are the usual celestial suspects, comets and asteroids. As comets streak through the inner solar system on their elongated orbits, the sun's heat vaporizes their icy surfaces, releasing not only gas but also countless grains of dust and rock, leaving behind their iconic tails. This dust becomes strewn along the comet's path, creating meteor showers when Earth passes through the debris stream. Similarly, asteroids constantly collide with one another in the main belt between Mars and Jupiter. These high-speed impacts are incredibly violent, grinding rocks into fine powder that gradually spreads throughout the solar system. For a long time, it seemed logical that these two sources alone could account for the zodiacal cloud. The dust particles, once liberated, spiral slowly inward toward the sun due to a subtle but relentless drag force known as the Poynting-Robertson effect, where the very pressure of sunlight itself robs them of orbital energy over millions of years. It's a cycle of creation and destruction that should, in theory, reach a steady state. However, when astronomers began to carefully measure the total mass and distribution of this interplanetary dust, they found a significant discrepancy. The calculated rate of dust production from known comet and asteroid activity doesn't seem sufficient to maintain the observed density of the cloud. It's as if you were trying to fill a leaky bucket with a slow trickle of water, yet the bucket remains mysteriously full. The dust is being destroyed or falling into the sun faster than these known sources appear to be replenishing it. This points toward the existence of a continuous and potentially major source of dust that we have not yet fully accounted for, a hidden reservoir that is constantly topping off the zodiacal cloud. One compelling hypothesis points the finger toward a specific family of asteroids. In the main asteroid belt, there are groups of asteroids that share similar orbits, believed to be the fragments of a much larger parent body that shattered in a catastrophic collision millions of years ago. The theory suggests that one or more of these asteroid families could still be actively grinding themselves down. The ongoing, low-level collisions between the fragments of this ancient breakup could be generating a steady stream of fresh dust at a rate that far exceeds normal asteroidal collisions. This would act as a persistent fountain of fine material, feeding the zodiacal cloud in a way that sporadic, individual asteroid impacts cannot. Yet, identifying the specific family responsible and confirming its current dust output has proven to be a challenging task. An even more intriguing possibility involves a journey from the solar system's frozen frontier. Some planetary scientists have proposed that a portion of the zodiacal dust might not be local to the inner solar system at all, but could instead be migrating inward from the Kuiper belt, that vast ring of icy bodies beyond Neptune. The mechanics of how this could work are complex. The combined gravitational tugs of the giant planets, particularly Jupiter and Saturn, can gradually perturb the orbits of the smallest Kuiper belt objects, sending them on chaotic journeys into the inner solar system where they eventually evaporate and disintegrate, contributing their dust to the cloud. This would represent a truly grand cosmic cycle, where material from the very edge of our planetary system slowly makes its way to the center, connecting the distant, dark realms with the bright, warm space near the sun. While a fascinating idea, the amount of dust that could realistically make this immense journey remains a topic of active research and debate. The mystery of the zodiacal light's origin is more than just an accounting problem. It's a window into the dynamic and ongoing evolution of our solar system. By understanding the balance of dust sources, we gain insight into the collision rates of asteroids, the activity of comets, and the gravitational pathways that transport material across vast distances. This faint glow is a testament to the fact that our cosmic neighborhood is not a static museum piece, but a living, breathing system where destruction and creation are constant, and where the gentle light we see on a clear, dark night is the visible signature of processes that have shaped and continue to shape the worlds around our star. Now consider a paradox not of distant galaxies or exotic particles, but one that strikes at the very heart of our own existence, rooted in the history of our home world and its life-giving star. Billions of years ago, when the first single-celled organisms were beginning to stir in Earth's ancient oceans, our planet should have been a frozen, lifeless ball of ice. This is the core of the faint young sun paradox, a profound contradiction between the solid evidence written in the most ancient rocks and the immutable laws of stellar physics. The problem begins with our understanding of how stars like the sun evolve. As a main sequence star fuses hydrogen into helium in its core, the core gradually becomes denser and hotter. This slow but steady increase in the star's internal temperature causes it to shine more brightly over billions of years. The models are exceptionally precise, telling us that when Earth was just a baby planet about 4 billion years ago, the sun's energy output was only about 70% of what it is today. That is a staggering difference. If you took our modern sun and dialed its brightness down by 30%, the calculations are unequivocal. The average temperature on Earth would plummet well below the freezing point of water. The entire planet, including the oceans, should have been locked in a global, permanent deep freeze, a condition from which it is difficult to see how life could have emerged. Yet the geological record screams the opposite. The most ancient rocks on Earth, known as the Isua supracrustal belt in Greenland, which are about 3.8 billion years old, show clear signs of having been formed in the presence of liquid water. They possess structures that could only have been created by sedimentary processes and by the interaction of rock with flowing water. Even more compelling is the evidence from around 3.4 billion years ago, where we find pristine examples of stromatolites, layered structures built by colonies of ancient cyanobacteria. These microorganisms thrived in shallow, sunlit seas, a scenario completely incompatible with a global ice age. The paradox is sharp and undeniable. The astrophysical models say freeze, but the rocks say swim. And Earth is not alone in this mystery. Rover missions to Mars have uncovered compelling evidence that the red planet, too, had flowing water and lakes on its surface during this same early period, despite being even farther from a fainter young sun. This suggests the paradox might be a fundamental feature of rocky planet evolution, not just a quirky episode in Earth's history. The primary and most widely accepted solution to this puzzle lies in the planet's primordial atmosphere. Today, we worry about an overabundance of greenhouse gases, but for the young Earth, a supercharged greenhouse effect may have been the very thing that saved it from an icy fate. The leading hypothesis points to much higher concentrations of gases like carbon dioxide and methane. In the absence of plant life and with vastly different geological activity, volcanic outgassing could have filled the air with CO2 at levels tens or even hundreds of times higher than today. This dense blanket of CO2 would have acted as an insulating layer, trapping the sun's faint heat with far greater efficiency and keeping the planet comfortably warm. Methane, an even more potent greenhouse gas, could have been produced in enormous quantities by early methanogenic microbes, adding another powerful layer to this planetary thermostat. However, while the greenhouse effect is a compelling answer, climate modelers have run into a persistent problem. It's often not enough. When scientists create sophisticated computer simulations of the early Earth's climate with high CO2 levels, they frequently find that it still doesn't raise the global temperature sufficiently to prevent the oceans from freezing, especially when factoring in that the young Earth's surface was probably darker, absorbing less sunlight. This gap between the model's predictions and the geological reality has forced researchers to consider other, more exotic factors that could have tipped the scales. One fascinating possibility involves the planet's rotation. Billions of years ago, Earth was spinning much faster, resulting in days that were only a few hours long. Some models suggest that these shorter days could have altered cloud formation and weather patterns in a way that reduced the planet's albedo or reflectivity, allowing it to absorb more of the sun's precious weak light. Another intriguing theory looks to the sky itself. Perhaps the young sun, though fainter in total brightness, was more active in other ways. It might have emitted a greater proportion of its energy in the form of ultraviolet light or been prone to more frequent and powerful solar flares. This different quality of light could have interacted with the early atmosphere in unique ways, perhaps heating it more effectively than visible light alone. There's also the speculative but captivating idea that Earth's early atmosphere contained ammonia, another powerful greenhouse gas, though it is easily broken down by sunlight and would have required a protective haze of other gases to persist. The faint young sun paradox, therefore, is far from solved. It stands as a humbling reminder that our models of planetary climate, even for our own world, are still incomplete. It challenges us to think more creatively about the complex interplay between a star's evolution and a planet's response. suggesting that the conditions that allowed life to gain a foothold were the result of a delicate and perhaps rare combination of astronomical, geological, and biological factors working in concert against the cosmic odds. Our journey now takes us to the very heart of our own cosmic city, the bustling, dynamic center of the Milky Way. This region, surrounding the supermassive black hole known as Sagittarius A star, is a maelstrom of stellar activity, powerful magnetic fields, and high-energy processes. It's a place we would naturally expect to be bright with high-energy radiation. But when scientists began analyzing data from the Fermi Gamma-Ray Space Telescope, which has been mapping the sky in gamma rays since 2008, they found a glow that was both expected and yet profoundly puzzling. There was a diffuse, persistent excess of gamma-ray light emanating from the galactic center, a haze of energy that extended thousands of light-years above and below the galactic plane. This signal, dubbed the galactic center excess, is there, it's real, but its origin has become one of the most hotly debated mysteries in modern astrophysics. The initial challenge was to subtract all the known sources of gamma rays. The galactic center is populated with pulsars, rapidly spinning neutron stars that beam radiation like cosmic lighthouses, as well as the remnants of supernova explosions and gas clouds being bombarded by cosmic rays. Once scientists meticulously modeled and removed the expected contributions from these well-understood objects, a significant and smooth residual glow remained. This excess wasn't clumpy or point-like, as you would expect from a collection of individual stars or remnants. It was remarkably symmetrical and extended, forming a broad, diffuse halo around the core of our galaxy. Its properties were strange. The energy spectrum of the gamma rays, their specific wavelengths and intensities, didn't perfectly match the signature of any known celestial particle accelerator. It was as if a secret, city-wide energy grid was operating right under our noses, powering a light whose source we couldn't identify. This is where the mystery takes a thrilling and controversial turn. The specific characteristics of this gamma-ray excess, its smooth distribution, and its particular energy spectrum happen to align surprisingly well with a theoretical prediction for the behavior of dark matter. According to some leading models, dark matter particles could be their own antimatter counterparts. If this is true, then when two of these particles collide, they would annihilate each other in a flash of energy, producing, among other things, gamma rays. The center of the galaxy is believed to be the region with the highest density of dark matter in the entire Milky Way, a vast, invisible concentration of this mysterious substance. Therefore, it would be the most likely place to see a high rate of such annihilations. The observed galactic center excess in this interpretation could be the first indirect detection of dark matter, the long-sought signal from the universe's most elusive component, a ghostly fireworks display happening in the darkness at the heart of our galaxy. However, extraordinary claims require extraordinary evidence, and the scientific community has vigorously pursued more conventional explanations. The primary alternative is far less exotic but still fascinating. What if the glow isn't from dark matter at all, but from a vast, unseen population of incredibly ancient stars? The leading candidate here is millisecond pulsars. These are neutron stars that have been spun up to incredible rotational speeds by siphoning material from a companion star. They are faint, stable, and emit a steady stream of gamma rays. Because they are so numerous and individually faint, the Fermi telescope might not be able to resolve them as distinct points of light from such a great distance. Instead, their combined, unresolved emission could blend together to create the very smooth, diffuse glow we observe. It would be like looking at a city from a high-flying airplane at night. From a distance, you see a uniform haze of light, but as you descend, that haze resolves into millions of individual streetlights and windows. The challenge is that we lack the instrumental resolution to descend and see if the galactic center's glow is indeed made of countless dim lights. The debate between these two ideas, dark matter annihilation versus a pulsar population, is intense and ongoing. Proponents of the pulsar theory point to recent analyses that suggest the excess might not be perfectly smooth after all. With more sophisticated statistical techniques, some researchers claim to see hints of faint clumping in the signal, a potential indication that it is composed of many point sources too faint to see individually, just as the city lights analogy would suggest. On the other hand, dark matter advocates argue that the energy spectrum of the excess still matches their predictions better than it does the typical emission from known millisecond pulsars. The truth is, both explanations face challenges. For dark matter, we have to accept the existence of a specific type of particle with just the right mass and interaction properties to produce the exact signal we see. For the pulsar explanation, we have to explain how such an immense population of these objects formed in the galactic center without leaving other obvious traces. This scientific detective story is far from over. The next chapter will likely be written by new and more powerful observatories. Gamma-ray telescopes with significantly better angular resolution could, in theory, finally resolve the excess into individual pulsars, confirming the stellar population hypothesis. Conversely, if the glow remains stubbornly smooth and diffuse even with sharper vision, the case for a dark matter origin would grow substantially stronger. The galactic center excess stands as a perfect example of science at the frontier, where a clear signal invites multiple compelling interpretations. It reminds us that the core of our own galaxy, a region we are now mapping with unprecedented detail, still holds profound secrets, forcing us to choose between the existence of a hidden city of ancient stars or the possibility that we are finally seeing the faint, annihilating glow of the universe's most dominant yet invisible substance. Moving out from the energetic heart of our galaxy, we venture into the cosmic countryside, into the silent, sprawling emptiness between the great walls and filaments of the universe's large-scale structure. If the superclusters of galaxies are the continent-spanning mountain ranges of the cosmos, then the voids are the corresponding oceanic abysses, regions of profound and startling nothingness. And none is more famous or more baffling than the Boötes Void. Discovered in the 1980s, this vast spherical region of space is not just empty, it is profoundly, almost unnervingly vacant. Stretching for a diameter of about 250 million light-years, if you placed our Milky Way galaxy at its center, the nearest edge of the void would be farther away than the Andromeda galaxy is from us. Within this incomprehensible volume, a space that could comfortably contain thousands of galaxies like our own, astronomers have found only a handful of galaxies, perhaps 60 or so where standard cosmological models would predict several thousand. It is a cosmic desert on a scale that defies easy comprehension, a giant hole in the Swiss cheese of the universe that seems to challenge the very principle that, on the largest scales, the cosmos should appear roughly the same in every direction. The existence of such a void creates a significant tension with our leading model of cosmic evolution, the lambda cold dark matter model. This model successfully explains the universe's web-like structure with its dense clusters and filaments of galaxies separated by emptier voids. The initial seeds for this structure are believed to have been planted by tiny quantum fluctuations in the density of the primordial universe, fluctuations that were then stretched to cosmic proportions by a period of hyper-fast expansion called inflation. Gravity then spent billions of years amplifying these slight overdensities into galaxies and clusters, while the underdense regions expanded and emptied out. The problem with the Boötes Void is one of scale. The initial fluctuations imprinted by inflation are thought to have been very similar in magnitude across space. For a void as enormous and as empty as Boötes to form through gravitational collapse alone, it would have required a primordial underdensity of a magnitude that is statistically extremely unlikely within our standard models. It's the equivalent of rolling a die and getting a 1 1,000 times in a row. It's not technically impossible, but it forces you to question whether you understand the rules of the game. This leads to a fundamental question. Is the Boötes void simply a statistical fluke, a rare but natural outlier in an otherwise homogeneous universe? In a cosmos as vast as ours, with billions of galaxies, perhaps we should expect to find a few truly enormous empty regions simply by chance. From this perspective, the void is not a crisis for cosmology, but a reminder of the sheer size of the playing field. The universe is under no obligation to be perfectly uniform in every single pocket. The cosmological principle describes an average condition, not an absolute rule for every cubic light year. Finding one such void might be surprising, but it doesn't necessarily break our models. However, if further surveys were to reveal that voids of this scale are more common than our simulations predict, then the fluke explanation would quickly lose its credibility, pointing instead toward a deeper issue with our understanding of the universe's initial conditions. This possibility opens the door to more exotic explanations. Perhaps our model of inflation, while incredibly successful, needs refinement. Could the process that blew up the infant universe have been more variable than we think? Some theoretical models suggest that inflation could have ended at slightly different times in different regions of space. A patch where inflation ended just a fraction of a second earlier than elsewhere would have had a tiny head start on expansion, leading to a region that is significantly larger and more diffuse than its surroundings, a prime candidate for becoming a giant void like Boötes. Alternatively, the void might be a signature of something even more peculiar happening in the early universe, such as a collision between two bubbles of spacetime during a multiverse inflation scenario, an event that could have carved out a vast, empty cavity. Another compelling line of thought involves the mysterious force we've already encountered, dark energy. We know dark energy is causing the expansion of the universe to accelerate, but what if its influence isn't perfectly uniform? What if the properties of dark energy itself vary slightly from region to region? In an area with a slightly stronger repulsive force, the expansion would be more vigorous, effectively pushing galaxies apart more efficiently and creating a larger, emptier void. The Boötes void could then be a window into the fundamental nature of dark energy, suggesting it is a dynamic field that can fluctuate rather than a constant force as represented by Einstein's cosmological constant. The sheer scale of the void forces us to consider that the forces shaping the cosmos may operate with a complexity we are only beginning to glimpse, and that these vast empty spaces are not mere absences, but active participants in the evolution of the universe, their emptiness sculpted by the most powerful and least understood energies in existence. But if the Boötes void represents an emptiness that challenges our assumptions about structure, the next mystery questions the very fabric of motion on the grandest scale imaginable. We are accustomed to things spinning, planets rotate on their axes, stars orbit within galaxies, and galaxies themselves slowly turn. But what about the universe as a whole? Could the entire cosmos have a net rotation, a preferred axis around which everything is subtly spinning? This idea, known as the universe's rotation, is one of the most radical and controversial frontiers in cosmology because, if true, it would fundamentally shatter a cornerstone principle of modern physics, the cosmological principle. This principle is not just a convenient assumption, it's the bedrock upon which almost all of our cosmic models are built. It states that, on the largest scales, the universe is both homogeneous and isotropic. Homogeneous means the universe has a uniform distribution of matter. No single point is special. Isotropic means it looks the same in every direction you look. There is no preferred orientation. This idea of a universe without a center or an edge is what allows us to apply Einstein's equations of general relativity to the cosmos as a whole. It's why we can talk about the universe expanding in all directions equally. The moment you introduce a universal rotation, you immediately violate isotropy. A spinning universe would have a special axis, a cosmic north and south pole. One direction would be fundamentally different from all others, privileging that axis of spin and creating a universe with a defined structure and orientation. The implications of such a discovery would be nothing short of revolutionary, forcing a complete rewrite of cosmology from the ground up. So, where would we even look for evidence of such a monumental spin? Astronomers have pursued this question by examining two key pieces of the cosmic puzzle. The first and most critical is the cosmic microwave background. The CMB is our most pristine snapshot of the infant universe, and it should be incredibly uniform. If the entire universe were rotating, however, this rotation would have imprinted a specific pattern on the CMB photons as they traveled through the spinning fabric of space-time for over 13 billion years. The effect predicted by general relativity is called cosmic birefringence. It would cause the polarization direction of the CMB light to be subtly twisted, creating a distinctive spiral pattern across the sky aligned with the axis of rotation. Teams analyzing data from the Planck satellite and other missions have searched meticulously for this telltale signature. To date, the overwhelming consensus is that no such pattern has been found at a level that would confirm a universal spin. The data is consistent with a non-rotating universe, which is a huge relief for the standard model of cosmology. However, a few studies have claimed to detect very faint, anomalous signals that could be interpreted as hints of a rotation, though these findings are typically at a low statistical significance and are hotly debated within the scientific community. They remain on the very edge of detection, tantalizing whispers that keep the idea alive as a speculative possibility. The second line of evidence involves looking at the universe in its present adult state. If the cosmos has a net rotation, that spin might have influenced the way galaxies formed and evolved. One might expect to see a preferred alignment in the rotation axes of spiral galaxies, with their spins tending to point in a particular direction correlated with the proposed universal axis. This is an incredibly difficult measurement to make, as it requires determining the true spin direction of millions of galaxies across vast distances and untangling that signal from local gravitational effects. So far, large-scale surveys have not found any convincing evidence for such a universal alignment. The spins of galaxies appear to be random, just as the cosmological principle would predict. Yet, there are always intriguing anomalies. Some studies of galaxy clusters have suggested peculiar, large-scale alignments of galaxy orientations over staggering distances, correlations that are difficult to explain through gravity alone. While these are far from proof of a universal rotation, they are the kind of oddities that prompt scientists to ask if there might be some deeper, underlying influence at work, a subtle guiding hand imprinted from the universe's very first moments. What could possibly cause an entire universe to rotate? The most logical place to look is the very beginning, during the inflationary epoch. Inflation is the theorized period of exponential expansion that smoothed and flattened the early universe. Could the quantum fields that drove this expansion have had a slight rotational component? It's a theoretical possibility, though most models of inflation are designed to produce a homogeneous and isotropic universe. A rotating universe would require a very specific and asymmetric set of initial conditions. Another, even more mind-bending possibility involves the universe's topology, its overall shape. If the universe is not simply infinite and flat, but has a complex, finite shape like a three-dimensional torus or a hypersphere, certain topologies could allow for rotation in a global sense without requiring a center. In such a universe, you could set off in one direction and eventually return to your starting point, and the entire structure could be spinning in a way that is consistent with its geometry. These ideas push the boundaries of theoretical physics into realms that are currently untestable, but they illustrate the profound theoretical shifts that would be necessary if evidence for rotation were ever found. For now, the idea of a rotating universe remains firmly in the realm of tantalizing speculation. The bulk of the evidence, particularly from the exquisite maps of the cosmic microwave background, strongly supports a cosmos that is, on the largest scales, isotropic and devoid of an overall spin. Yet the persistence of a few anomalous signals and the profound implications of the idea ensure that it remains an active, if niche, area of inquiry. It represents the ultimate test of our foundational principles, a question that probes the deepest nature of reality. The search for a universal rotation is a testament to science's willingness to question its most cherished assumptions, to actively look for evidence that could overturn the entire paradigm, because it is in those extreme possibilities that we sometimes find the most profound truth. From the fleeting whisper of the wow signal to the immense, silent pull of the Great Attractor, from the ghostly presence of dark matter to the bizarre geometry of the Red Rectangle Nebula, our journey has taken us across an almost unimaginable spectrum of cosmic mysteries. We have confronted phenomena that challenge our understanding of scale, from the subatomic fury of ultra-high-energy cosmic rays to the billion light-year emptiness of the Boötes void. We have seen how the universe defies our expectations at every turn, presenting us with perfect hexagons on a gas giant, a moon that once had a magnetic field it should not have possessed, and a fundamental constant of expansion that refuses to give us a single, consistent answer. This incredible diversity of unanswered questions is not a catalogue of science's failures. On the contrary, it is a vibrant map of its most exciting frontiers. Each of these 25 enigmas represents a boundary of human knowledge, a line in the sand drawn by the cosmos, daring us to cross it. They are the puzzles that propel entire fields of science forward, inspiring new technologies, new theories, and new generations of curious minds. The fact that we can even identify these mysteries, that we have the tools and the intellect to perceive these profound gaps in our understanding, is a testament to how far we have come. The silence of the Fermi paradox, the tension in the Hubble constant, the strange trajectory of Oumuamua, these are not dead ends, they are invitations. They are the cosmic equivalent of a locked door, behind which we can hear the faint sounds of marvelous and unknown mechanisms. The struggle to find the key to pick that lock is where the most thrilling discoveries are born. It is in the process of wrestling with the unknown that we often stumble upon truths far more wonderful than anything we could have invented. So the next time you find yourself under a clear night sky, take a moment to truly look up. See not just the pinpricks of light, but the profound darkness between them. In that darkness resides everything we do not know, every mystery waiting for its solver. Remember that the universe is under no obligation to make sense to us, but we are under a beautiful obligation to try and make sense of it. The greatest adventures in understanding are not confined to the history books. They are happening right now in the data streams of telescopes, in the equations on a theorist's chalkboard, and in the simple human act of wondering what lies beyond. Stay curious, for the cosmos has only just begun to